elevational shift on a mountain sedge. He's from the Institute of Alpine Environment from the EURAC in Bozen. Please.
Thanks for the introduction. I'm here today to present my master thesis on how the resident vegetation can modify the climate-driven elevational shift of a mountain sedge. To begin, let's go back to the start when everything began. It is some years ago now that we got contacted by a botanist from Germany who spent her holidays in the Upper Vinschgau. And she had noticed our monitoring stations there in the Mazia Valley. And she contacted us because she had conducted the research for her master thesis of the year 1976 in the same area and asked us if we would be interested to see her historical data. And of course we have been. And so sometime later she came to visit us and showed us her thesis containing lots of old vegetation records and old historical pictures and lots of data. And that's how I got to the basis for my thesis. You see here a historic occurrence mapping of the species Carex humilis in the Mazia Valley. This mapping defines the upper elevational range limits of the species for the year 1976. It are 304 occurrences. And yeah, she recorded them while her systematic walks through the hillside. And I thought this would be a good topic for my master thesis 2 years ago. And so finally I started to georeference and digitalize the data. And I began with some background research on the topic. The study area is the Mazia Valley in the north and south Tyrol. It is an inner alpine dry valley characterized by pastures, montane and subalpine conifer forests, and in the higher altitudes with alpine, subalpine grassland. The study species is Carex humilis. It is a warm and heat-loving perennial hemicryptophyte, and it's mostly found on exposed crusts and south on exposed hillsides. It loves warm, dry, shallow, and nutrient-poor sites, and is not very competitive. And so while my first trial works, I already have seen that there have been some differences, and so I began to work out some hypotheses. First of all, I expected the species to shift in elevation at the leading and maybe also at the trailing edge due to the recent climate change. Further, I expected that the resident species of the study area was slowing down or at least affecting the elevational range expansion of the study species. And I expect the study species to be less likely at sites with higher competition and therefore also with higher vegetation cover, as the species is not very competitive. After 3 weeks of hard work then in the field, I had finished my mapping. In total, I mapped 1,255 sites with absences and presences. And in the lower altitudes, I tried to follow the historical mapping routes, but as in the higher altitudes, it got a bit more difficult due to the steeper terrain, and I tried to follow the ESA lines. This is already the point where we got the first results. And we see here in black the historical occurrences, which also have been mapped in 2018. So we have lost nearly no sites. I just eliminated the others because it would be too complicated to understand. So we have the black sites, which have been found in 1976 and 2018, and the greens have been the new found sites in 2018. And we used a rather conservative way to calculate the species shift. We used the average 30 highest occurrences for each year and compared the values, and it resulted in a 250-meter shift in the last 42 years, which means a 51-meter shift per decade. This is something that might be wrong in the program you got, because I calculated another time and I saw that there have been made a mistake. I still don't know why, but it happened. And at the same time, there had not been detected a shift of the trailing edge because the species have still found at the bottom of the valley. But as you can see, we have quite big differences. At the entry of the valley, we have a smaller shift than in the middle of the valley, where it's quite big. And this is the reason why we expected the resident vegetation to have an influence on these shifts. For this reason, we use the species distribution model in R to calculate the historic distribution of the species. So basically, we use the historic distribution, historic species data, plus the environmental data of the study area. In our case, we use the aspect, the slope inclination, the curvature, the mean annual solar radiation, and a climatic predictor. Here we have used a bioclim variable. It is the mean temperature of the warmest quarter of the year for the years 1943 until 1977 averaged. And from this data, the species distribution model then calculated the ecological niche of the species and projected it onto our study area, resulting in a simulation for the distribution for the year 1976. By updating the climatic parameter to the current climatic conditions, which means the temperature increased by 1.13 degrees Celsius. The model also predicted how the species should have changed its range since 1976 under the influence of the current climate change. This prediction then has been used and has been compared with the mapping I have conducted, resulting in this a bit chaotic map. But basically, it are presences and absences, and divided into two subsets. We have once the triangles for sites that have not been predicted to be suitable by the species distribution model, and we have the circles that have been predicted to be suitable for the species by the species distribution model. And basically, we mainly wanted to focus on the sites predicted, and here especially on the yellow circles, where a prediction has been predicted since 1976, but the population, the sites have not been populated by the species so far, and we wanted now to know what are the reasons for this. Therefore, we have chosen some vegetation data. We had two data sets. Once the rasterized distribution maps of the four most common dwarf shrubs in the species, Rhododendron ferrugineum, Vaccinium myrtillus, and Vaccinovitis idea, and Calluna vulgaris. And additionally, as an indicator for the general vegetation cover, the normalized difference vegetation index, NDVI. And to assess whether these indicators are meaningful indicators, we compared the sites with presences of Carex humilis and absences of Carex humilis in terms of the NDVI and the average competitor species cover for the sites predicted to be suitable for the species. And as you can see here in the table on the right, all four indicators have shown significant differences between sites where Carex humilis has been absent and where it has been present. In the graph, you see on the y-axis the average competitor species cover, and on the x-axis, sites where Carex humilis has been absent and were present. For all the three indicators, in blue, Calluna vulgaris, Rhododendron ferrugineum in green, and the two Vaccinium species in gray. And yeah, it's visible that Carex humilis occurred much more often on sites where the vegetation cover was much lower. Similar results for the NDVI. We see on the y-axis the probability of occurrence for Carex humilis, and on the x-axis the NDVI, increasing from left to right. The upper dots stand for presences and the lower dots for the absences. And as you can see, the highest probability of occurrence for the species is between values of 0.4 and 0.5, which are medium or average to low, as values of 0.2 are like bare rock, and 0.6 are, and upwards are forests. And you can see that from 0.6 on, the probability to find the species is falling steep. And now that we knew that the indicators are meaningful, we focused more on potential new colonization events. So basically we used the same data set as before, but we eliminated all the sites that have already been colonized in the year 1976 in base of the species distribution model, which simulated the extent of that year. And we have evaluated these sites then by means of two multiple logistic regression models. One for sites that have been predicted to be suitable for the species, and one for sites that have not been predicted to be suitable for the species. Yeah, the table again shows that the NDVI proved to be the most important factor regarding the absence or presence of the species, while Rhododendron ferrugineum had a negative effect, or is negatively correlated to the species at sites that are potentially not suitable. But in this case, this might be due to the different habitat preferences, and there might not be causal relation. And we have found also that the two vaccinium species are correlated negatively on potentially suitable sites and correlated positively on potentially negative sites, which is also an effect that has been found in Norway for Carex bigelowi in combination with other dwarf shrubs. And to come back to one of the first slides, a little conclusion. We have found that the species has shifted upslope 250 meters at the leading edge, but did not shift at the trailing edge. So furthermore, we have found that the resident vegetation and the competitive interactions with the resident vegetation have influenced the species range expansion dynamics significantly. And third, we have found that Carex humilis was found at sites with significantly lower competitor cover. Yeah. And last but not least, I wanted to thank especially Mrs. Wimkoff for providing us the data and for allowing me to use it as basis for my thesis. And I also wanted to thank Andreas Hilpold for his help during the fieldwork, and the Autonomous Province of Bolzano, which financed the LTSR Open Air Laboratory in Machatal, in which this resampling has been enabled. Thank you for your attention.
Thank you very much, Harald Crepaz, for this talk. Are there questions? Any questions? Yeah, please.
Thank you very much for the presentation. At the end, I didn't get it really. Is your species distribution model working well, or do you have to consider the competitive effects? So if you are using the species distribution based on the environmental variables, is it enough, let's say, or is it very inappropriate without considering the competitive effects?
As indicator for the quality of the species distribution model, we used the true skill statistic, and there we reached a value of 0.87, which is quite excellent, so the model worked very fine. First, we wanted to use more variables, but the problem is that the most climatic variables have been correlated too strongly, so we had to choose fewer ones. But in general, the model worked very well.
Are there other questions? No more questions around?
Ja, also ich bin's nochmal. So sorry, it was in English.
German is fine too.
No, you said the species distribution modeling is working and you have a lot of data. So I'm wondering if there is any evidence of an accelerated increase of the species distribution range as the climate change is also accelerating. Can you model that with your data?
I don't think that there's some evidence, but when you take a look at this map, we see that we have a lot of correctly predicted sites here in the middle, and we have also sites above this line that have not been predicted to be suitable for the species, but still have been populated by the species. So it could be an indicator that the species shifted its extent upward faster than it should, but I'm not sure if it's just a question of predictors or not. But when considering the climatic data, the species shifted 215 meters, and at the same time the annual mean temperature increased by 0.8 degrees or something in 40 years. When taking in consideration that usually the species or the temperature diminishes by 0.6 degrees per 100 meters, it's quite over, it extends its slope, its range faster than it should have, slightly.
Okay. Another question? If not, we are continuing. Thank you very much for this talk and for the discussion. And last but not least, I would like to invite Yuri Nascimbene from the Università di Bologna. Lui parlerà su pattern di diversità multitaxon lungo gradienti altitudinali nelle Alpi e nel massiccio della Maiella. Prego, Yuri.